Welcome to The Explainer. You've probably wondered how an AI is actually built, right? Well, today we're going under the hood to see how trillions of words scattered all across the internet get forged into a single coherent intelligence. Let's dive in. So, how do you even begin to do that? I think the best way to wrap our heads around it is to imagine we're taking a tour of a massive AI factory. We're going to follow the entire assembly line, from the raw materials all the way to that finished product you chat with every day. Okay, so the very first stop in our AI factory is all about forging the raw materials. I mean, we've got to take the completely chaotic, unstructured text of the entire web and turn it into a language the machine can actually process and understand. And that whole process kicks off with something called tokenization. See, computers don't read words like we do. They crunch numbers. So all that text gets chopped up into these fundamental little units called tokens. A simple phrase like "hello world" gets translated into a sequence of numbers, maybe something like 42808, that the model can finally work with. Okay, but here's where it gets really clever. How does the AI even build its vocabulary? Well, it uses this brilliant algorithm called byte-pair encoding. It starts super simple, with just individual characters. It looks for the most common pair, like in this example, A, and merges them into a brand new token. Then it just scans again, finds the next most common pair, and merges those. You repeat this process millions and millions of times, and you end up building a massive, rich vocabulary from the ground up. And what you get from all this is a super efficient, universal vocabulary. It's amazing, really, because it's built from the byte level up. The model can understand common words, sure, but also rare words, misspellings, programming code, even emojis, all without ever getting stuck on some unknown character. All right, so our raw materials are forged and tokenized. Now we move to the main assembly line. This is the pre-training phase. This is where the model actually learns, well, everything. So to learn about the world, the model is fed this carefully blended diet of text. The bulk of it, yeah, it comes from general web pages. But it's also supplemented with a whole library of books to learn narrative, conversational text from places like Reddit to learn dialogue, and even super specialized data like code and scientific papers to learn how to reason. But listen, you can't just dump the entire internet into the machine and call it a day. That data has to be rigorously cleaned. And one of the most critical steps here is deduplication. Why? It's simple, really. If the model sees the exact same piece of text thousands of times, it's just going to memorize it. It won't learn the underlying patterns, which is the whole point. And that brings us to the absolute core of the learning process, pre-training. For months on end, on thousands of incredibly powerful GPUs, the model has one single simple goal: predict the next word in a sentence. Now that might sound too simple, right? But by doing this trillions of times, it's forced to build this incredibly complex internal model of how language works. It's implicitly learning grammar, facts, and even styles of reasoning, all just to get better at that one simple task. I mean, the scale here is just staggering. A model like GPT-3 has 175 billion parameters. You can think of these as tiny little adjustable knobs or connections inside a giant brain. The whole pre-training process is just about tuning every single one of those knobs to create a statistical map of all human language. And what you get at the end is what we call a base model. Now, this base model is incredibly knowledgeable, for sure, but it's not a helpful assistant yet, not even close. It's more like a text completion engine. So now it's time for the alignment phase. This is where we teach it how to actually be useful. And this slide just brilliantly illustrates the difference. If you ask a base model, what is the capital of France, it might just spit out another question. It's just continuing the pattern it sees. But the aligned model, it understands your intent. It knows you're asking a question and it gives you the answer. So the first step to get there is something called supervised fine-tuning, or SFT for short. You can think of this like giving the model a course in How to Be a Good Assistant 101. We basically show it thousands of high-quality examples of prompts and the perfect answers, teaching it the conversational format that we all expect. But to teach it real nuance, to get it to understand what's not just correct, but also helpful and safe, we use a process called reinforcement learning from human feedback, or RLHF. It's this fascinating three-step dance. First, humans just rank different AI responses. They look at a few options and just pick the one they like best. Then, and this is the cool part, a separate AI, called a reward model, is trained to predict what those human preferences will be. So the really crucial point here is this. We're using slow, careful, qualitative human judgment to train a fast, quantitative AI judge. This reward model can then give the main LLM instant feedback on millions of examples, constantly steering it to produce answers that are more helpful, more harmless, and more honest. And it can do all of this at machine speed. Okay, so now we have a smart, helpful, and aligned model. Awesome. But how in the world do we get it to answer your questions in milliseconds? This is the final challenge on our factory tour, optimizing for inference, or in other words, making it fast. Every single time you get a response, it's actually happening in two distinct phases. The first is called prefill. That's where the model processes your entire prompt all at once. It's super fast and compute heavy. Then comes the decode phase, where it generates the answer, one token at a time. And that's a much slower, more sequential process. So what's the secret to making that one token at a time decoding fast? It's a clever trick called the KV cache. Think of it like the model's short-term memory. It stores all the key calculations from the tokens that came before it, so it doesn't have to reread and recalculate the entire conversation every single time it generates the next word. It is an absolute game changer for speed. And how does it actually choose that next word? Well, it uses a decoding strategy, and there's always a trade-off here. A greedy search just picks the most likely word. It's precise, factual, but it can be kind of boring and repetitive. But if you increase the temperature or use a sampling method like top P, you add a bit of randomness. That makes the output more creative, but also potentially less accurate. And finally, to make these absolutely giant models actually fit onto today's hardware, we use a technique called quantization. It basically reduces the precision of the model's numbers, which dramatically shrinks its memory footprint. I mean, look at this. Moving from 16-bit to 4-bit precision can cut the memory usage by a massive 75%, and it does it with surprisingly little impact on the model's performance. But building the AI isn't the end of the factory tour. A responsible builder also has to understand and plan for the product's inherent flaws and limitations. This is quality control. And let's be clear, these models have well-known failure modes. They can hallucinate, basically just make things up. They can absorb and then amplify the societal biases that are already present in their training data. And they can be manipulated by clever users, prompt injection, to bypass their safety instructions. These are really significant ongoing challenges that the entire field is working on. And this all brings us to the final and most crucial question that developers are grappling with every single day. We've gone from this chaotic mess of raw internet text all the way to a machine that can talk like us. But the next great challenge is making sure we can truly trust what it has to say.